Ampere's circuital law. Now let's see the second most important law in magnetostatics, that is called as Ampere's circuital law. Here the definition states that the line integral of the magnetic field intensity H vector around a closed path is equal to the total current enclosed by the path. Just recall the Gauss law which you had in the electrostatics, which states that the total flux coming out of a surface is equal to total charge enclosed by the surface. Okay, so you are having some charge which will emit flux. So the total flux is equal to total charge in the surface. That is Gauss law of electrostatics. Similarly, we are defining Ampere's circuit law here. The magnetic field around a closed path is equal to the total current. Okay, there the source is charge, here the source is current. Okay, there electric flux, here magnetic field density or magnetic flux. Okay, so in statement wise, you can tell closed integral of H dot dl is equal to I enclosed, and this is special form of the fundamental law, biot-savart's law. Okay, by taking biot-savart law, okay, you can define Ampere's circuital law as a special form of biot-savart's law. This one is also known as integral form of Ampere's law, similar to Gauss law of electrostatics. Okay, here consider a current carrying element, okay, which is placed along the z-axis. The blue line is the current carrying conductor which carries current I. Okay, and here in order to calculate the current in the carrier, okay, let's draw a imaginary path called as Amperian path around the conductor. And if you know the field density in this path, then using that you can calculate the current in this current carrying conductor. That is the usage of Ampere's law. And Ampere's law greatly reduces the complexity to calculate the magnetic field. That is the biggest advantage of Ampere's circuital law, but it is having its own limitation. That is, it can be applied only if the current distribution is symmetrical. Condition is symmetrical, then only you can apply the Ampere's circuital law. If the current distribution is not a symmetrical one, then you have to apply the biot-savart law only, no other option. Now, let's try to formulate the Ampere's circuit law in its point form as well as in its integral form. Okay, the current in terms of current density can be written as I enclosed. Okay, I enclosed is equal to surface integral of J dot ds. Okay, if you know the current density, by taking surface integral of this, you can get the total current. Okay, now let's equate equation 1, that is I enclosed is equal to closed line integral of H dot dl is equal to I enclosed. Now both the equations 1, 2 having I enclosed as a one of the term, so the remaining terms must be equal. So closed line integral of H dot dl is equal to surface integral of J dot ds. Okay, and now let's take the second part, first part alone. Okay, in the left side alone. Okay, we know that the Stokes theorem relates line integral with surface integral, line integral with surface integral. Okay, so using this, suppose you are having a line integral, closed line integral of H dot dl, means by using curl you can define its surface integral, that is closed line surface integral of del cross H dot ds is equal to closed integral of H dot dl. Okay, now compare 3 and 4, so that you will have surface integral of J dot ds is equal to surface integral of del cross H dot ds. Here in this equation, you are having integral s, here also surface integral, here you are having ds, here also ds, a dot product, a dot product. So the remaining terms must be equal. So del cross H must be equal to J. Del cross H must be equal to J. This is known as point form or differential form of Ampere's law, and this one is most popularly known as Maxwell's third equation for static fields. Static fields. Okay. In matrix form, you can write J vector is Ax, Ay, Az, dou by dou x, dou by dou y, dou by dou z, Hx, Hy, Hz is that the magnitudes of H vector along the x-axis, y-axis, and z-axis. This is in rectangular coordinates. Similarly, you can write the equation in other coordinates as well, like cylindrical or spherical coordinates. Now let's see some problems based on Ampere's circuital law. Determine the current density for a magnetic field density of H vector that is equal to 28 sin x ay amperes per meter. From Ampere's circuital law in differential form, we know that J vector is equal to del cross H vector. Here H vector is given. We need to find current density, that is J vector. So J vector which relates H vector is J is del cross H. So Ax, Ay, Az, dou by dou x, dou by dou y, dou by dou z, Hx, Hy, Hc. Just substitute the values. Here it is having only Ay component. So the remaining are 0. It is 28 sin x. So if we expand this, you will get 28 cos x AC amperes per meter square. Second problem, in cylindrical coordinates, the magnetic field density is given by H vector is equal to 2 rho minus rho square A pi vector amperes meter for rho 0 to 1. Determine the current density as a function of rho with the cylinder. What is the total current passing through the surface z equals 0 for rho is 0 to 1 in AZ direction. Verify the same using Stokes theorem. Okay, so from Ampere's circuital law in differential form in cylindrical coordinates, J vector is del cross H that is equal to 1 by rho rho A pi Az dou by dou by dou pi dou by dou c H rho H pi Hz. Okay, so here the values given only along A pi, so H pi only given. Just substitute the value. Okay, that is 2 rho minus rho square. Remaining two quantities are 0. Okay, so if we expand this, you will get J vector is 1 by rho 4 rho minus 3 rho square Az, and the unit is amperes per meter square. And second part, what is the total current passing through the surface z equals 0 for rho is 0 to 1 in Az direction. So we know that the current density and current is related by using the equation I, that is surface integral of J dot ds. Here ds is along the surface d is equals 0 means, so rho d pi Az vector. So J dot ds is J we already calculated in the previous part. Okay, 4 minus 3 rho Az, and ds is rho d pi Az. Just take dot product. So Az will cancel. You will get 4 minus 3 rho d pi. So this one is J dot ds. Now we need I. So I is integral of this. So integral 0 to 2 pi, that is the limit for pi, and integral 0 to 1, that is limit rho is given 0 to 1. So 4 rho minus 3 rho square d rho d pi. If you integrate this, finally you will get 2 pi. If you substitute pi is 3.14, you will get I is 2 pi amperes, that is 6.28 amperes. Okay, and the last part, verify the same using Stokes theorem. The Stokes theorem states that closed integral of h dot dl is equal to surface integral of del cross h vector dot ds, that is surface integral of j dot ds. Okay, so surface integral of h dot dl is integral 0 to 2 pi j dot ds we already have. Just substitute that one here, and rho is 1 here. Okay, So I is 0 to 2 pi, 2 minus 1 pi d pi, that is pi 0 to 2 pi. So 2 pi minus 0, it is 2 pi. So current I is 2 pi. So using Stokes theorem also, we got the same result, that is 6.28 ampere. Hence, the Stokes theorem got verified.